So what we're going to start with is chapter 5, and this is going to be about integrals. And so we'll just start at the beginning of chapter 5. All of it's going to revolve around integrals, but first we have to figure out the area under a curve. So section 5.1, areas and distance. So first off, the area problem. So what is area? What do we mean when we talk about area, and how do we find it? So this is kind of the area problem. We have a graph, and as you can see, here's our graph. I have just y equals f of x, nothing fancy. We're looking at just a regular curve. So you can see this curve right here. What we mean when we mean area is we mean the area under the curve or the area between the curve and the x-axis. And it's always going to be the x-axis. I mean, you could talk about the area under a curve and the curve is underneath the x-axis. So, if we had something like maybe this curve, the area under the curve is always the area between the curve and the x-axis. So when we talk about area, that's what we're talking about. So you can see that kind of depicted here in the letter S. So speaking of area, we know the area of a few different shapes. We know the area of a rectangle, that's just length times width, and that's actually going to come into play. And we know the area of a triangle. So the area of a triangle, 1/2 base times height. If you know those two things, then you can actually pretty easily approximate the area under a curve, and that's what we're going to do. So really the only two areas you need to know for right now are the area of a rectangle and the area of a square. Sorry, area of a square, a rectangle and the area of a triangle. So it's not necessarily easy to do this, and so that's what we're going to be approximating. So we'll give you an example here. We are looking at the area under the parabola y equals x squared from 0 to 1. So you can see this area, it's S here. We're looking from 0 to 1, and I want to know what's the area underneath that curve. So one thing that we want to note is that the area is definitely bigger than 0, right? There is some area, but also that area is less than 1. And the reason I know it's less than 1 is just imagine if this was actually a triangle. Or you can imagine if this was a square to make it even bigger. I mean, what's the area of that square? Well, it would be base, which base is 1, the height was 1. So the area of this square is 1. So the area is definitely between 0 and 1. Even more than that, you could say the area is between 0 and 1/2. Because if you think about this triangle that I've just made, the area of that triangle is 1/2, because 1/2 times base times height. So the area is definitely going to be between 0 and 1/2. We're going to try to approximate it. So what I can do is let's just imagine the x-axis, and let's imagine that I break that into 4 different pieces. So each piece, because it originally had 1, when I break it up into 4 different pieces, all those pieces are going to have, area 1/4. So I had my tablet is on right here. I had my original 0 to 1. I'm going to break this into 4 different pieces, and so now my numbers are going to be 1/4, 1/2, and 3/4, and I know that the width of each of these is 1/4, and that's going to be important to us. From there, I'm going to draw the vertical pieces accounting to all those endpoints. So that's what these lines are. So all the vertical pieces accounting for all of my endpoints. And you can see that here. And now I have 4 different regions. I have S1, S2, S3, and S4. And if I can figure out an approximation for each of those, then I can add them up to get a total approximate area. So one thing I can do is I can look at everything on the right. So if you think about this first interval here, I can figure out the area of the rectangle by using the endpoint that was on the right. So the endpoint that was on the right was 1/4. And now what's the height of this rectangle? Well, that comes from my function. And the function was y equals x squared. So this will be 1/4 squared. So the area of my first rectangle would be base, which is 1/4. times the height, which was 1/4 squared. For my second rectangle, so let me see here. Let's do, here's S2. We're again going to pick the point on the right. So my endpoints are 1/4 and 1/2. 1/2 is on the right. So then the height is coming from this line, which is 1/2 squared, because that's my y value. So 1/2 squared. So now S2 would be base. So the width of that rectangle was 1/4 times height, which is 1/2 squared. And I could keep doing this, right? S3, I'm looking at the endpoint that's on the right, so that would be 3/4, and the 3/4 gives me the height of the rectangle by plugging it into the function. So the function was x squared, so 3/4 squared. And then lastly, this last rectangle, the height of it's 1, 1 squared is 1, so the total area here is 1/4. 1/4 times 1 squared, so 1/4. So what I can do is add all of those up. Right, here was my S1, here was my S2, here was my S3, here was my S4. I add all those up and I get 0.469, which is probably, a pretty good estimate. I knew that it was going to be between 0 and 0.5, right? The 0.5 was kind of an overestimate. So now I know that it's definitely above 0, and I know that it's definitely below 0.46875. Now, how do I know that it's strictly less than? Well, let's go back to this picture one more time. You see all this blue? All of this blue stuff is what we just added up, but we added up too much, right? All of this area shouldn't have been there. That was an overestimation. So I know that the approximation that we just got was a little bit too big. So I know that the true area is less than that number. So now what we could do is, instead of looking at those right endpoints, what happens if we look at those left endpoints? So instead of the right, let's look at the left. So if I look at my first little interval here, the width of that is still 1/4. But now the height, I'm going to use the left-hand endpoint. So the left hand was 0. So I'm going to plug that into my function. So I get 0. For S2, the width of that rectangle is still 1/4. But now the height is given by whatever was on the left, plugging that into the function. So 1/4 times 1/4 squared, whatever that is. We'll figure out in the next window. And you would keep doing this, right? Each one is going to be 1/4 times whatever the left value is squared, because that was the function. Now, if you look at this, is this going to be an overestimate or an underestimate? So remember, we're trying to figure out the area under the curve. What we're doing is we're adding up all these blue pieces. So it looks like this is going to be an underestimate when we figure it out. So I plug those in, and these little rectangles are just multiplication. Plug all that in, and I got 0.21875. And that was an underestimate, like we said. So now we know that the area is somewhere between 0.21875 and 0.46875. To get an even better estimate, I could just keep dividing that interval into more and more rectangles. So instead of just having 4 rectangles, what happens if we have, more than that? So what happens if we have 8 rectangles? So here is my right-hand approximation. Over here I have my left-hand approximation. The right-hand approximation, you can see it has all this extra blue stuff, so this is going to be an over approximation. On the left, I'm missing some areas, right? I'm missing these areas. So this is going to be an under approximation. You can do those calculations if you want. In fact, I think that would be a very good exercise for you to do. But these are the two values you get, so 0.73 and 0.398. And how you would go about doing those, well, here you're going to have, S1, S2, S3, etc. I'll do S1 and S2 for you on the right. Now each rectangle is going to have width 1/8. So all of them are going to be 1/8 times something. This would be 1/4, then 3/8, and then 1/2, etc. For the height of that first rectangle, it's coming from the right-hand endpoint, so 1/8 squared. For my next one, it's coming from, again, the right endpoint, so that would be 1/4, so 1/4 squared. You'd figure out all 8 of those, add them up. Over here for the left, the width is still 1/8, but now we're looking at the x value that's on the left-hand side of the interval. So for my first interval, the value on the left is 0. For my second interval, the value on the left is 1/8. And you would find out all 8 of those and then add them up, so that you don't have to do it. Here are a lot of different values. So if you look at, if I did 10 rectangles, the left hand was 0.285, the right hand value was 0.385. You would not want to do that by hand, right? 10 is kind of a lot. If I did 20, now the left hand is 0.309 and then 0.359. And then if I go all the way down here to 1,000, so let's say that I broke that interval from 0 to 1, I broke that into 1,000 different pieces. Each piece had a rectangle. If I added all of those rectangles up on the left and added all of them up on the right, you can see that on the left I get 0.3328, on the right I get 0.338. So it looks like something is happening, because if you look at these numbers, the right-hand values are kind of decreasing to a number. The left-hand values are kind of increasing as we go down this. And it looks like they're going towards the same number. So our guess will be that the area is approximately 0.33 repeating. And this is kind of pictorially what we're doing here. So if I only had 10 intervals, then I have, my 10 rectangles I would add up. If n was equal to 30, I have 30 different rectangles. If n is equal to 50, I have 50 different rectangles. But what you see is that the more rectangles I have, the closer the approximation. That those rectangles are actually giving you a pretty good estimate of what's underneath the curve. So we define the area. So this is actually a definition. We define the area to be the limit of the sums of the areas of approximating rectangles. So that's a lot. All this is saying is that if you look at the right-hand limits, so the right-handed summation, and assume you did infinitely many rectangles, that's what this is saying. So this limit as n approaches infinity of r sub n, that's saying you want to do infinitely many subintervals, so infinitely many rectangles, and you look at the right-handed limit, so the right-handed summation, that's equal to the limit as n approaches infinity of the left-handed summation. So they're approaching the same thing. One is approaching it from below, one is approaching it from the left. Just depends on what your graph looks like as to which one's going which direction. But those two summations that we looked at, if you increase the number of rectangles to infinity, they're the same, and that's equal to the area. So we're going to do this generically, right? We're not going to work with just one function. The whole x squared thing is just an example to give you an idea of what's going on. We want to look at this for any function, and we want to be able to develop nice formulas for it. So the first thing we need is we're going to define delta x. So I don't know if you've seen deltas before, if I have any Greek fraternity or sorority students here, but delta means change in math. So when I say delta x, I'm talking about the change in x. If you think about that one example we did from 0 to 1, when we broke it into 4 pieces, the width of each subinterval was 1/4. So all delta x is it's the change from one endpoint to another once you break it down. So each of these is going to have widths delta x. And the way you find delta x is you take your rightmost endpoint, so b, minus your leftmost endpoint, a, and divide it by however many subintervals you want. So if you go back to the very first one that we did, we went from 0 to 1. So a was equal to 0, b was equal to 1. So it'd be 1 minus 0. We broke it down into 4 subintervals. So the width of each subinterval is 1/4. That's your delta x. So it's the width of each subinterval. Once you have that, then we can figure out our endpoints. So our first endpoint is a. Our last endpoint is b. To figure out all the endpoints in between, all we do is add delta x. So you'll add one of the delta x's, then add two of your delta x's, all the way up to get to b. So if we're thinking about that first example that we did, it went from 0 to 1, and we had delta x was equal to 1/4. So the first thing I would do is add 1/4, then I would add 1/4 again, then I would add 1/4 again until I get to my b. That's all we're doing. So we're just adding that delta x until you get to b. And then once we get that, we can get a really good approximation. For my right-hand endpoint, or my right-hand approximation, you're going to be starting with x1. And then your next right-hand endpoint will be x2. Your next one's x3. You're going to keep going until the right hand of the very last interval, and that right-hand side is b. So to figure out the area, you would do delta x, so length or base, times your height, and your height is f of that endpoint. For my second one, it's going to be delta x times f of x2, and I would just keep adding this up, and that's how we get this formula. So your right-hand approximation is f of x1 times delta x plus f of x2 times delta x, and you keep going from there. And you can kind of see these pictures here. The more rectangles you get, better the approximation. For my left-hand limit now, let me go back to that picture. For my left-hand side, if I'm looking at this first interval, I'm not going to plug in x1 to my function to get the height. I'm going to plug in a. And I'm not going to plug in b to get the height of that last rectangle. I'm going to get whatever x was previous to that, so x n minus 1. And that's where this function comes, or this equation comes from. So for my left-hand sum, my left summation, I'm going to be doing the same thing. The base was given by delta x, the height was given by the function. But now I'm plugging in x0. Remember, x0 was the same as a, so x0 is a. And I'm going to plug in the very last x that came before b. So this was the x before b. And here's a picture of another thing we could do. You know, instead of just looking at left endpoints and right endpoints, what if we just picked any point between the two? I mean, you can do that. So here's one way. You could just use sample points. It doesn't really matter. We just need a way to figure out the height of the rectangle. I already know the width of all these rectangles. The widths of all these rectangles are delta x. We're just trying to figure out the heights. And there's a good way to write this. It's called sigma notation. So sigma notation, sigma just means sum. So we're just adding up a bunch of stuff. At the bottom, this tells you where to start. At the top, it tells you where to end. So for this first one, I'm saying add up the following, starting with I equals 1 all the way to I equals n. So add up f of xi delta x. So start with I equals 1, then go to I equals 2, then I equals 3. Stop when you get to I equals n. And there are a few different summations that we should probably know. I'm going to show them to you now. One that you should know is if I do from x equals 1 to n of 1. So let's think about what this means for a second, and let me do a more concrete example. I'll do it here. Let's say that I'm doing from I equals 1 to 3 of 1. This says I'm going to start with I equals 1 and add up 1. Then I'll move to I equals 2. I'll add up 1 again. Then I'll move to I equals 3, and I'll add up 1 again. And now I stop, because this top number was 3 that told me to stop. So I add that up, and I just get 3. So if you're looking for the sum from I equals 1 to n of just 1, that value is n. The next one that I need to know, I equals 1 to n of I. this actually has a nice formula for it. So let me give you an example. Let's say I was going from I equals 1 to 3 again of I. So I'll start with I equals 1, plug that into my formula. Well, the formula is just I, so it would be 1. Then I'll go to I equals 2, plug that in. It would just be 2. And then lastly, we're going to stop right after this one because I equals 3. So I get 1 plus 2 plus 3, which is 6. And there's actually a nice formula for this. It's n times n plus 1 over 2. So if I add up n numbers, so 1, 2, 3, 4 to whatever, that value is actually n times n plus 1 over 2. So these are 3 summations that you should know. If we're adding up I squared, and I'll give you an example of that in just a second, it's n times n plus 1 times 2n plus 1 over 6. If I'm adding up 1 n times, it's n. If I'm adding up I to n, it would be n times n plus 1 over 2. So for example, let's do that other one. If I go from I equals 1 to 3 of I squared. So first I'll start with I equals 1. 1 squared is 1. Then I'll go to I equals 2, so 2 squared. Then I equals 3, and I stop at I equals 3 because it told me to stop there. I get 3 squared. So what is that? That's 1 plus 4, which is 5, plus 9, which is 14. Which just so happens to be 3 times 4 times 7 over 6. Which is weird. You wouldn't expect that to happen, but it is. So there are your 3 formulas that we should know for summations. We are going to skip distance for right now, just to be aware, but we will come back for it.